most of us trust numbers. In biology and medicine, biostatistics act as a referee, deciding whether a new drug really works or whether a gene actually causes disease. But what if the numbers mislead you? What if statistics show one thing, but the truth is something else? Today, we are exploring knife science to reveal 3 of the strangest and most surprising biostatistical anomalies. Get ready to be amazed. Let's get started. Let's start with a medical classic, the Simpson's paradox. Imagine you need a risky surgery. You pull up the stats for 2 hospitals in your city to see which one has the best survival rate. At Hospital A, 90 of the 100 patients survive surgery. That is a 90% success rate. At Hospital B, 80 of the 100 patients survive surgery. And 80% success rate. So, do you choose Hospital A right away? Wait, not so fast. If you look more closely and separate the data by patient condition, comparing the critically ill patient with the healthy ones, you will notice something strange. For mildly ill patients, Hospital A has a 99% success rate, whereas Hospital B has a 99.5% success rate. For critically ill patients, Hospital A reports a 30% success rate, while Hospital B reports a 40% success rate. So, why does Hospital A loses in both cases, yet seem better overall? The real reason is patient severity. 35.87% of the patients that Hospital B takes in are more critically ill, lowering its average, while around 30.04% of the patients that Hospital A takes in are critically ill. Add all the data together and the truth is hidden by the average. Next, let's talk about Berkson's fallacy. This is a weird situation where unrelated diseases seem connected just because of where the data came from. Imagine you are conducting a study on 2 newly discovered conditions. One of them is called disease X and the other one is known as disease Y. You find a weird, shocking correlation. Patients who have disease X are much less likely to have disease Y. Does disease X protect you from disease Y? Have you uncovered it in medical miracle? Not quite. This is the Berkson's fallacy. This happens because hospital data is biased. Admitted patients are already sick, so it can seem like disease X and disease Y rarely occurs together. But outside of that, it is not true. Such bias routinely tricks researchers. Now, the strangest anomaly of all of this, and it is the base rate fallacy, a biostatistical problem that can cost lives. Suppose a screening test for a rare virus is 99% accurate. Your result is positive. So, what is the real chance you are infected? Most people say 99%. But biostatistics reveals a different picture. If the virus is very rare, affecting only 1 in 10,000, the math changes. A 1% false positive rate means many more healthy people than sick, so false positives outnumber the true cases. For example, assume the prevalence of disease X is 1 in 10,000 and the population is 1 million. There should be 100 cases. If the test sensitivity and specificity are both 99%, then the distribution of cases is shown like this. We can see that when the prevalence is low, then the false positive rate is very high. If you apply a Bayesian calculation, your odds of infection are about 1%. Highly accurate tests can be deceptive if diseases are rare, highlighting why base rates matter. These 3 biostatistical anomalies reveal how statistics can fool us. Hidden factors and biases means biology's numbers require context. And that is about it for this video. Thanks for watching.